So we're going to look at the mean and standard deviation of a binomial random variable. And this is developed on page 390 of your textbook. Page 390. All right, so the mean is n times p. The standard deviation will be the square root of n times p times 1 minus p, where n is the number of trials and p is the probability of success on any trial. So let's do a check for example 4. N was 5, and the probability of success on any trial was 0.25. That's because there were 4 answers to choose from. And so the average of x equals 5 times 0.25, which is 1.25. And the standard deviation is the square root of 5 times 0.25 times 0.75, which is 0.968. So we're looking on to the next example. So here we have an engineer chooses an SRS, and you'll recall that that stands for a simple random sample of 10 switches from a shipment of 10,000 switches. Suppose that 10% of the switches in the shipment are bad. However, the engineer is not aware of this statistic. The engineer decides to estimate the percentage of bad switches in the shipment by counting the number of bad switches in his sample. So is this a binomial setting? So I'd like you to pause now and see what you think. All right, so is this a binomial setting? And if we think about bins, is it binary? Yes, it is. The sample is either good or bad. We'll come back to I in a minute. Do we have a fixed number of samples? Yes, we do. We've chosen 10. And is the probability of success for each case the same? Well, we'll come to that in a minute as well. So let's look at the independence again. And in this case, we do not replace the switch after each sample, so it's not strictly independent. So we'll jot that down. No, we do not replace the switch after each sample. We take 10 switches at a time. So it is not strictly independent. But the sample is small compared to the population, so we can assume independence. So I'll repeat that. Sample is small compared to the population, So we can assume independence. For instance, if I randomly reached into a big, huge vat of balls and pulled one out and then threw it back in, the chances of me collecting that one again would probably be pretty small on my next draw. So we can assume that the fact that I left it out is not going to affect my results. So we'll put a star next to I, and we'll say that yes, the probability is basically the same for each sample. So what is the probability then, if we can use the binomial setting, if we can assume that it's basically a binomial setting, what is the probability of getting no defects? So probability of no defects is going to be 10, because that's how many we're choosing. Choose 0. And in this case, we know that what the probability of each one being bad is 1 over 10. And we're saying none of those. And the probability that was of defects, the probability of defects is 1 over 10, so 9 out of 10, no defects, and we're hoping for 10 of those. And when we work this out, we get 35%. So sampling without replacement condition. So that was what our last example was. So here we're assuming independence. Whoops, sorry. Let us assume independence. So when taking an SRS of size n, lowercase n, from a population of size big N, we can use the binomial distribution to model the count of successes in the sample as long as little n is less than or equal to 1/10 of big N. So as long as our sample is smaller than 1/10 the population. All right, let's look at example number 6. And this is our last example on binomial distributions. An airline has just finished training 25 first officers, 15 male and 10 female, to become captains. Unfortunately, only 8 captain positions are available right now. Airline managers decide to use a lottery to determine which pilots will fill the available positions. Of the 8 captains chosen, 5 are female and 3 are male. Explain why the probability that 5 female pilots are chosen in a fair lottery is not equal to this. So let's have a look. We will look at, first of all, is this a binomial setting? So looking at bins. Do we have binary outcome? Yes, we do. The person is either male or female. Is it independent? In this case, it is not independent. We don't replace the people. I'll repeat, not independent. We don't replace the people. And, however, we just learned that sometimes we can assume the situation, because if we have a large enough population and the sample size is small in comparison. But let's have a look. In this case, we can't assume independence, since the sample, which was 8, is more than 1/10 of the population n, big N, of 25. So if we had chosen just 2 people, then we could have calculated the probability in this manner. And note, we will not cover the normal approximation to the binomial distribution at this time, so that's pages 395 to 397. This homework we will deal with in class, so you do not need to look at those questions before our lesson, next lesson. And that concludes the session on binomial distribution. Have a good day.